In the first two lectures of Chapter 3, we focused on the concept of phase stability, phase transformation, phase equilibrium, and phase diagram for pure, simple substances. In Chapter 2, we discussed the spontaneity of phase transformations and learned that under certain conditions, crystallization of a substance is spontaneous, while under other conditions, melting is spontaneous. Whether crystallization or melting occurs depends on the relative pressure and temperature. Spontaneity of an isothermal and isobaric process can be predicted if one calculates the change in Gibbs energy for the process. Hence, if one knows the enthalpy change, entropy change, and temperature. In Chapter 1, we learned that melting, vaporization, and sublimation are endothermic processes. Hence, they are also associated with an increase in entropy for the system and a decrease in entropy for the surroundings. Conversely, crystallization, condensation, and vapor deposition are exothermic processes. Hence, they are associated with a decrease in entropy, increase in order of the system, and an increase in entropy of the surroundings. In this chapter, we investigate analogous processes that are ubiquitous in the life sciences, such as protein folding and denaturation, membrane crystallization, DNA zipping or unzipping, and so on and so forth. We will see that such processes, like the classical phase changes, also exhibit changes in enthalpy and changes in entropy. Hence, they can be treated in similar fashion as phase changes. We start today's lecture with a brief discussion showing that a number of order-disorder transitions in biosystems exhibit similar characteristics as pure substances undergoing phase change. We then discuss the principle of operation of the differential scanning calorimetry techniques, since this technique allows the measurement of enthalpy changes and characteristic temperatures of order-disorder transitions. We then examine how this calorimetric technique can allow us to study the thermal denaturation of proteins and the melting behavior of DNA. Subsequently, we discuss the crystal to liquid crystal transition observed in lipid bilayer membranes and review how the characteristic transition temperature of a membrane can be affected structurally or chemically and reflect the change in thermal stability of a cell membrane. We finished the first part of Chapter 3 by discussing protein crystal and crystal structure. When we discussed phase transitions in Chapter 2, we emphasized that one of their characteristics was the dramatic increase in disorder that takes place at the melting and boiling point of any substance. Melting and vaporization are endothermic processes, during which intermolecular interactions are dramatically altered, as in the fusion process, or for the most part eliminated, as in the vaporization or sublimation processes. While these transitions are associated with a decrease in intermolecular interactions, they are also associated with an increase in entropy. The disruption of favorable intermolecular interactions is always associated with an increase in disorder, since entropy and enthalpy changes must be of the same sign. Think about the relationship delta S equals delta H divided by T. Similarly, we can talk about the increase in order, negative delta S, accompanying the lowering of the enthalpy and energy, negative delta H and delta U, associated with crystallization, condensation, or vapor deposition processes. The same arguments can be made when studying the order-disorder transitions in lipid bilayer structures, proteins, and DNA. In the case of proteins, disruption of hydrogen bonding, hydrophobic and ionic interactions, lead to loss of secondary and tertiary structures, and unfolding as the temperature is raised sufficiently. A similar disordering is observed in the double helix of DNA as the temperature is raised. Note that these order-disorder processes are not only triggered by changes in temperature, they can also be induced by changes in pressure and in the life sciences, changes in pH, use of denaturants, and so on.